Sorry about the abrupt change, but I suddenly realized that I wanted to go over and switch to my lecture, which I think talks about optimization. This is actually out of my data-driven decision-making class. And this entire field of making decisions comes out of operations research, and that's that you're using analytical methods to make the best decision. And where this really started to become a field of interest in science was World War II. For example, where's the best place that I should deploy radar in order to cover everything? When I mine shipping lanes, where is the right place? When I put out landmines, what's the right pattern? Naturally, I need a certain randomness, but what's too close, what's too much, and plus the landmines cost money. I want to use the smallest number. MIT was a very big player in this in World War II, in this field. And so, why is it worth... oh, excuse me. Yeah, I know these lectures kind of suck in some ways because I think I'm dying of terminal cold. But anyway, the data allows you to make sense of things, it simplifies things, and it becomes a toolbox that you can use to make decisions. It's used in a lot of different areas, whether they're networks, business, science and engineering, or game theory. How do you respond to things? There are three basic parts to these systems. There are the decision variables. Those are the attributes. These are the things that drive decisions, whether it's time or money or weight. There's an objective function, and that defines how these relationships are tied into the objection you want. And then there are constraints, and constraints limit to how varied this variable should be. Otherwise, if we say, I want to make the maximum profit, then what's the computer going to come back and say? You want to make a maximum profit? Make an infinite number of widgets. And so here's an example problem for you. A company builds stone and tiles. They make $1 profit on stones and $3 on tiles. It takes a half day to make a stone tile, where it only takes a day to make a regular tile. And they want to know what's the most profitable mix between these two. And I'm limited to 90 days. So what I can do is set it up. As you can see, my objective function that's maximizing the profit is $1 times the number of stone tiles I'm going to make plus $3 times the number of regular tiles I can make. That's what I want to maximize. However, it's limited to the fact that S, which is the number of stone tiles I'm going to make, the quantity, times a half a day plus the number of regular tiles I'm going to make, times 1 day, or 1. What's the maximum? So the big Q there is going to tell me what that number is. Well, how should I solve this? And the way you can solve it, actually, I've got it in the lecture, is to use a program in Excel called Solver. Now for some of you, you may not have Solver on your Excel. It's an add-in. So you go to the add-in tab and you can find it. What Solver does is it does linear programming, and it actually optimizes things. So we're talking about that variable Z. What do I set the objective to? And what I do is I set it to maximum. I want to maximize it. What cells am I going to change? This is S and T. And then you have a number of constraints. And I actually have too many constraints here. But the values have to be, I have to have 0. I can't have negative tiles. I can't owe people tiles. So that's a constraint. And then you could see the 90 days. And so Solver has a number of different models. For linear models like this, set it to simplex linear programming, and then you would hit the solve button. And what would happen is Excel would spit out a bunch of files for you. And so, as you could see here, it figures out the volumes. And the volumes it's saying is, don't bother making any S's, make T's. All 90 of them. Does that make sense? Yeah, it does make sense. Why? Because you're earning 3 times more profit, but it only takes twice as long. So there is no advantage in terms of time. Here's another example. If I have just simple algebra that I need to maximize. And so this is how I would set it up on that algebra in Solver. I'll leave that for you to fool around with. When it says a variable is non-binding, it means it's not going to really affect the outcome. Solver also gives you sensitivity, and those sensitivities tell you how much you can vary, and the solution won't change. So I can increase x by 3 or decrease it by 3.67. So if I change my algebraic equation to 25.5 plus 21 plus 20 x, I come up with exactly the same solution. There's more than one equation that describes a solution. And what shadow price means is that for every 1 that I change, I get 11 in return. And so these sensitivities help you figure out how much you can vary things. And it also has a physical meaning. The physical meaning is if it tells me, like for example, if I can expand my capacity for number of tiles by 1, that I can get $90 back. I'm just speaking hypothetically. Then I start thinking, hey, maybe I should invest in that. So you have right-hand side changes. Those are the changes in your constraints. But the sensitivity report nicely gives you the limits of how you can change these variables. Now, in terms of simulation, what if you don't like the result? And that's that when you look at your function, your max function, you can change the coefficients. What are those coefficients? Well, $1 per tile and $3 per tile. Well, supposing I really want to make stone tiles because it's easy, then guess what? I need to find a way to make it more profitable. I can change the constraints, and those are typically like production goals. What if I add more machines? Things change. And tell me my new product cost. There are a bunch of different kind of programs. I'll just leave this to look at. And also, an example of optimization programs is investment. What do you want to do in investment? You want to maximize the return, but minimize the variance. And so you can make programs to do this, to do those calculations, and figure out the mix of what different kinds of stocks you want to buy.